Alright, so we now have enough information, enough knowledge of the periodic table and the elements that we can take an element, we can ionize an element predictably, and now we are going to see how we can combine them to make molecules for the first time. So buckle up, here we go. Okay, so just to recap quite quickly, we have these noble gases. These noble gases are noble because of the fact that they have a complete outer shell of electrons. This offers them great stability. So they have, everything is good and right in the world for them. Conversely, we have elements that are either have too many electrons and would like to give them up, or we have elements that don't have quite enough electrons and would like to gain a few so that they also can have their complete outer shell of electrons. So let's go over an example of forming a molecule from two elements. And so we can start from sodium metal. Sodium metal is right here. And sodium metal would love to, in its neutral state, has 11 electrons, and would love to lose one electron to become a sodium cation, a sodium positive charged ion. It wants to have 10 electrons because neon has 10 electrons. Neon has a completely full outer octet shell. So conversely, we have chlorine gas. So chlorine gas. Chlorine sits right here on the periodic table, and chlorine has, in its neutral state, 17 electrons. It would love to have 18 electrons, just like argon, its adjacent neighbor. And so it can absorb an electron, become a chloride anion, a chloride, a negatively charged ion, and it can get 18 electrons, which makes it the same electronics as a noble gas. And so once sodium loses an electron and once chlorine gains an electron, they both are very happy, but they also are bothly charged. And we know, of course, that positive and negatively charged species are attracted to one another. And so now what we have is we have sodium ions and chloride ions that are going to kind of be glued to one another. And they're going to be glued together via an ion bond, or we're going to call it an ionic bond. You can kind of see they form this lattice structure of positive, minus, positive, minus, positive, minus that are electrostatically held together. And in the macroscopic way, we call this Na plus Cl minus, or sodium chloride, or table salt. Okay, so let's do this again, but let's do this from the perspective of a Lewis dot structure. So we're still looking at sodium chloride, we're still looking at table salt here, and we can look at the neutral form of sodium right here. Sodium, and this has one too many electrons to be happy. This would prefer to have just its octet, its outer shell full, not having one too many. And so we can ionize sodium to form sodium plus, or sodium cation. Conversely, chlorine in its elemental form has 7 electrons and would love to absorb one more electron, and in doing so would become a chlorine anion. And typically these processes are not separate of one another. So we can do is we can actually can draw, for instance, the electron from sodium actually migrating to the chlorine. So sodium is actually going to donate its electron to be happy, to give it to chlorine, which is also going to be happy. And now what we're going to have is we're going to have sodium, which is going to be electrostatically attracted to a chlorine anion. Okay, so some important points to talk about when we're talking about ionic compounds or ionic molecules. So ionic compounds, of course, always contain positive and negative ions. And so when we're talking about stuff like sodium chloride, we have Na plus Cl minus, and there could be lots of variants of this. We could do something like magnesium. Magnesium forms 2 plus. Oxide forms 2 minus, right? And so there's always a positive and always a negative. In a formula, the sum of the charges always equals 0. So generally, these ions will combine to make sure that they have a neutral end product. So a great example of this might be magnesium chloride. So magnesium needs to get rid of 2 electrons to form a stable octet, so it's 2 plus. Chlorine needs to get rid of 1 electron, so it's Cl minus 1. And so if we were to combine these to form an ionic compound, we would say that, well, this is 2 plus and this is a single minus, so to balance this out, we would do something like that. MgCl2, we need 2 chlorines to balance the positive 2 charge of magnesium. So, and the last one is the formula represents the smallest ratio possible. So if you looked at the previous diagram of table salt, you saw that there was thousands of sodium and chlorides alternating in a huge lattice. So and that's reality. That's what the sodium chloride table salt looks like. But we're not gonna write Na 5000 chlorine 5000 because that's stupid. No, we're gonna represent this molecule with the smallest ratio possible. The smallest ratio that still gives us all the information, has a balanced sum of charges, and uses positive and negative ions. And so, of course, in this case, we're going to represent this as 1 sodium and 1 chloride. Okay, so there are some pretty commonly encountered ions. So when you're generating different ionic molecules from these ionized elements, one thing is that you simply can look where it is in the periodic table and figure out what the charge should be. So if you're an alkali metal, then you need to lose 1 electron. So all of these are typically positive 1. Conversely, if you're an alkali earth metal, you need to lose 2 electrons, and that means that you're typically plus 2. If you jump over from magnesium 12 to aluminum 13, you can see here that aluminum wants to lose all 3 of its outer shell electrons so that it becomes a positively 3 charge. And at this point, you're kind of halfway distance. So if you look right here, this is where carbon is, and so carbon can either jump 1, 2, 3, 4 times, or it can jump 1, 2, 3, 4 times to go the other direction. So it's kind of halfway, and as such, it doesn't really predictably form either one. However, when you go to the other side of carbon, now we have the halogens, and the halogens, of course, are going to be some element that takes on 1 extra electron to be happy. If we move on 1 more beyond that, then now we're talking about the chalcogens, and these are oxygen, sulfur, selenium, tellurium. These things would like to jump 2 spaces. They'd like to take 2 electrons to have a full outer shell, so they become 2 minuses. And then we have the pnictogens. These is nitrogen and phosphorus, and then these are going to take a 3 minus charge, so that they can be happy. They're going to take 3 electrons, so they can get their outer shell completely filled. Okay, so let's try a practice problem here. Let's figure out the formula for lithium oxide. And so let's kind of figure out what's going on here. So lithium is a alkali metal. It has 1 electron, and so ideally, with this lithium chooses to form lithium positive, it loses that electron. Oxygen, on the other hand, if we look at the periodic table, it has 6 valence electrons. So the faster route for oxygen is to actually gain 2 electrons to be O2 minus. And so when we're combining lithium and oxygen together, we have lithium with a positive 1 charge, and it's happy, it's stable, and we have oxygen with a minus 2 charge, happy and stable. And so we would draw maybe something like this. LiO, or I'm sorry, Li2O. My apologies. So Li2O, and this is a balanced molecule right there. Okay, so how about magnesium oxide, MgO? Well, so magnesium is in the alkali earth metals, and this has 2 electrons that it would love to get rid of. So it's going to form a positively 2 charged magnesium, and they're just going to lose both of the electrons. And once again, oxygen is in the chalcogens, and it would love to absorb 2 electrons and form a completely filled octet, 2 minus. And so when we combine these, we would say something perhaps like magnesium 2 plus combines with oxygen 2 minus, or we would say magnesium oxide. And if you didn't like my chicken scratching on the previous page, you can kind of get a cleaner view of the problem right here. The lithium giving its electrons to the oxygen, or the magnesium giving its electrons to that oxygen to form these stable octet full species that are charged, and then combining the species together and so that they have an equal and neutral sum of charges.